Hi, my name is Jenny Huynh, and today I will be presenting the topological optimization of EV battery enclosures in high-impact loads. Designing a battery pack enclosure that could withstand high-speed crash loads while reducing weight results in higher safety for electric vehicles. Vehicle performance is dependent on the lithium-ion batteries. If the battery packs are subjected to deformation from external factors, it could lead to combustion and render the vehicle useless. In Figure 1, the battery pack is installed underneath the front seats of the vehicle, which is important to understand how location affects the battery enclosure during crashes. Some highlights from the related work regarding the EV battery enclosure includes understanding what makes lithium-ion batteries fail. Vibration and heat are external factors from crash loads that can create these failures. Implementing dampeners and thermal management is integral to creating a better battery enclosure. Creating an optimized structure using a topology study can also create a lightweight structural design. Furthermore, proper material selection can reduce the weight of the structure while reducing the deformation by 300% during crash loads. After some understanding of where the EV battery packs are located, we can dive into the objective of the project, which is ultimately to design an enclosure for high-impact loads. This will be achieved using topology optimization and proper material selection. By using finite element analysis to plot the deformation versus applied load, the enclosure can be designed to be robust and lightweight. Material selection and battery placement within the enclosure are also integral additions to reducing deformation in the lithium-ion batteries. A few major deliverables that will be coming out of this project will include providing a scale model with appropriate composite materials used, providing a plot of deformation versus applied force, providing 3D CAD files of the battery enclosure, and lastly, to provide a test fixture to model the scale crash load simulations. Evaluation metrics are important to determine whether the project is successful. There are three major metrics that we adhere to. First is having high mechanical strength, which means a deformation of 1 millimeter or less. This will indicate how protected the lithium-ion battery is from impact. Second, low frequency vibrations, vibrations that are under 100 hertz. This metric is important because the laminate between the structure of lithium-ion batteries begins to separate at 100 hertz, which would cause the battery to become unstable. Lastly, maximize vehicle's crash load safety rating while minimizing the weight. This means battery enclosure weight reduction by 30%. This is the metric applied to the topology study. To begin the research, I would predict the deformation behavior of the battery enclosure by using max applied force at different locations. Then determine areas that can be reduced in weight and apply simulations with different composite materials. Next would be to create regression modeling and response services to determine the correlation between composite materials, applied force, and deformation. Finally, a prototype 1 to 10 scale model would be created using a low-fidelity 3D printer for a scale model testing. Various resources that will be needed would be a 3D printer, various composite materials, a test fixture, a high-speed camera, a test lab, and obviously the SolidWorks and ANSYS software. One big concern with this project would be the long lead time of material procurement for different composite materials. A plan to combat this is to perform extensive finite element analysis on the models to predict the behavior of the composite materials, and then procure at least one or two of those required materials, such as carbon fiber PLA. Some preliminary work that has already been done for this project was the research and design of the battery enclosure, initial FEA simulations of simplified geometry for the battery enclosure, and the production of a 1 to 10 scale model. For the preliminary research and design of the battery enclosure, we took a look at the size of lithium-ion battery packs inside of a Tesla Model S. Each battery module consists of 444 lithium-ion batteries. Understanding how each module was installed assisted with determining the initial FEA analysis. FEA simulation of the simplified battery enclosure geometry is displayed below. These were the deformation results for front-loaded applied force of 6,800 Newton meters. The maximum displacement observed was 0.4134 millimeters. This condition would be considered a passing metric, and this area could be structurally optimized during the research. These were the deformation results for the side-loaded applied force of 6,800 Newton meters. The maximum displacement observed here was 0.3203 millimeters. This condition would also be considered a passing metric, and this area could be structurally optimized during the research. This research is important because electric vehicles will be the future of transportation. This research can assist with weight reduction within vehicles, saving batteries, which means saving the environment because we're creating less waste, and also improving the safety measures for consumers who use electric vehicles. Here are my references. Thank you for participating in my presentation today.